In the basic concepts of chemistry, we have to see how to calculate the empirical formulas and molecular formulas of compounds. What do you mean by empirical formula? It gives the formula of a compound in the simplified atomic ratio of corresponding elements, whereas a molecular formula gives the exact number of atoms present in a molecule. Say for example, the molecular formula of glucose is represented as C6H12O6. For the same compound, empirical formula means we have to take the simplified atomic ratio. In glucose, carbon, hydrogen and oxygen atoms are present in the ratio 6:12:6. Therefore, simplified atomic ratio is 1:2:1. So, in that manner, if you represent the formula, CH2O will become empirical formula, whereas C6H12O6 becomes molecular formula. So, how can you correlate empirical formula and molecular formula? The relation is molecular formula is equal to empirical formula into some n integer value. This integer value can be calculated by using the relation gram molecular weight by empirical formula weight. In general, we get fractional values only. Those fractional values are to be adjusted to the nearest integers, and when you multiply empirical formula with that adjusted integer value, you will get molecular formula. So, let us see some examples of how to find out empirical formula and molecular formula of a given compound. The empirical formula of a compound is given as CH2O. It is mentioned that its molecular weight is 90. We have to find out what is the molecular formula. So, the relation to be used is molecular formula is equal to empirical formula into n factor. This n factor can be calculated by using the relation gram molecular weight by empirical formula weight. Gram molecular weight is specified as 90. Empirical formula weight we have to calculate from the empirical formula just like molecular weight. Empirical formula is given as CH2O. So, corresponding weight comes out to 12 plus 2 plus 16, that is 30. So, empirical formula weight is 30, it comes out to 3, a perfect integer. Therefore, molecular formula is equal to, we can write CH2O taken 3 times or C3H6O3. This is another model in the calculation of empirical formula problems. Sometimes they may give the percentage composition and you will be asked to calculate the empirical formula or molecular formula of the compound. Then we have to follow a standard format like this: serial number, percentage composition of elements, atomic ratio, simple atomic ratio. Simple atomic ratio in short is called as SAR. Atomic ratio in short is called as AR. Now, in the given problem, 3 elements are specified. One is carbon, another one is hydrogen, and third element is chlorine. Before proceeding to the next stage, we have to check the total of percentage composition. If it is equal to 100, we can proceed further. If it is not equal to 100, you take the difference as equal to percentage of oxygen, whether it is specified in the problem or not. In this case, the total comes out to 100%. So, we can continue to the next stage. In order to calculate the atomic ratio of individual elements, we have to divide the percentage composition with the concerned elements atomic weight. Say for example, carbon's atomic ratio will be 10.06 by 12, where 12 is the gram atomic weight of carbon. That of hydrogen is 0.84 by 1 and that of chlorine is 89.10 by 35.5. 35.5 is the atomic weight of chlorine. On calculation, these values come out to, once you get the atomic ratio values, you can proceed to the next stage, that is calculation of simple atomic ratio. In the atomic ratio, you will come across various values. Select the least value and with that divide all other values. The ratio obtained is called as a simple atomic ratio. Say for example, here in the atomic ratio you came across 0.83, 0.84 and 2.5. So, the least value is 0.83. With this we have to divide all other values. So, in the simple atomic ratio column, 0.83 by 0.83, 0.84 by 0.83, 2.5 by 0.83. This value comes out to 1, second value also comes out to 1 approximately, the third value comes out to 3 approximately. So, those adjusted integer values will be taken as a simple atomic ratio. Therefore, empirical formula of the compound can be represented as C1H1Cl3, or it can be represented in a simple manner as CHCl3. In this way, when percentage composition of elements is specified, we can calculate the empirical formula and molecular formula of the compounds. Balance this given equation by ion electron method. The given equation is Cr2O7 - 2 plus SO2 gives Cr plus 3 plus SO4 minus 2, and the arrow mark H plus ion is written, means this reaction is taking place in acidic medium. In order to balance this equation, first we have to write down the oxidation states of elements other than oxygen and hydrogen. Other than oxygen and hydrogen, the elements present in this equation are chromium and sulfur. Here chromium oxidation state comes out to +6, sulfur +4. On the product side, chromium oxidation state is +3, sulfur oxidation state is +6. So, for chromium there is a decrease in oxidation state from +6 to +3, whereas for sulfur there is an increase in oxidation state from +4 to +6. Wherever there is a decrease in oxidation state will be called as reduction half reaction, and wherever there is increase in oxidation state will be called as oxidation half reaction. Now, separating the two half reactions, while balancing these half reactions, the sequence order to be followed is element first, oxygen, hydrogen followed by charge. In this half reaction, the element other than oxygen and hydrogen present is chromium. On the reactant side, 2 chromium atoms are present, whereas on the product side only 1 is present. So, multiply the product side with 2, then the element is balanced. Next, balancing of oxygen. On the reactant side 7 oxygen atoms are present, on product side no oxygen atoms are present. So, as per the rule, on the deficient side we balance oxygen by adding required number of water molecules. In this case that number is 7. Now, oxygen is balanced. Next, to balance hydrogen we have to check the medium of the reaction. In the given equation on the arrow mark it is mentioned as H plus, means the reaction is taking place in acidic medium. On the product side 14 hydrogens are present, the reactant side is deficient by 14 hydrogens. So, as per the rule we write 14 H plus ions. Now, hydrogen is balanced. Now, to balance the charge we have to consider the difference in oxidation states. Cr2O7 minus 2 plus 14H plus 6 electrons gives 2Cr plus 3 plus 7H2. Now, charge is balanced. Apply the same procedure for the second half reaction also. The element is sulfur, which is already balanced. Coming to balancing of oxygen, reactant side is deficient by 2 oxygens. So, it is balanced by adding 2 water molecules. Then oxygen, on reactant side 4 hydrogens are present, product side no hydrogens. So, hydrogen is balanced by adding required number of H plus ions, because reaction is taking place in acidic medium. Now, to balance charge, consider the change in oxidation state, which is 2 units. As it is oxidation, the difference is indicated on the product side. Now, we have to add the 2 half reactions. Before adding, the number of electrons should be made equal in both the half reactions. For that purpose, multiply this entire equation with 3. It comes out to 3SO2 plus 6H2O gives 3SO4 minus 2 plus 12H plus 6 electrons. Adding the 2 half reactions, whatever is common on opposite sides they get cancelled. So, finally Cr2O7 minus 2 plus 3SO2 plus 14 hydrogens, 12 hydrogens are present. So, 2H plus gives 2Cr plus 3 plus 3SO4 minus 2 plus 1 water molecule. This will be the completely balanced equation. Balance this equation by ion electron method. The given equation is P4 plus OH minus gives PH3 plus HbO2 minus. In this equation, OH minus is present as one of the reactant. So, we should consider this reaction as if taking place in basic medium. Now, as usual, we have to calculate the oxidation states of elements other than oxygen and hydrogen. Here the element present is phosphorus. On the reactant side, oxidation state of phosphorus is 0, because it is a homoatomic molecule. In the products, in phosphine, oxidation state of phosphorus will be -3, and in this HbO2 minus ion it will be +2. So, for phosphorus there is a decrease in oxidation state, which can be taken as a reduction half reaction. For same phosphorus there is increase in oxidation state, which can be taken as oxidation half reaction. Such type of reactions are known as disproportionation reactions because same substance on the reactant side is undergoing both reduction as well as oxidation. Now, divide the given equation into two half reactions, namely reduction half reaction and oxidation half reaction. The reduction half reaction is P4 gives PH3. Oxidation half reaction is P4 gives HPO2 minus. Now, the sequence order of balancing of equation is element, oxygen, hydrogen and then charge. Here the element phosphorus on reactant side 4 atoms are present, on product side only 1 atom is present. Hence, multiply with 4. Element is balanced. Now, to balance oxygen, there is no oxygen, that means it is balanced. Coming to balancing of hydrogen, on the product side 12 hydrogens are present, on reactant side no hydrogens and the reaction is taking place in basic medium. Therefore, on the deficient side first we will add required number of water molecules, on the opposite side equal number of OH minus ions. With this, hydrogen is balanced. Now, for balancing of charges, consider the change in oxidation state. For phosphorus, it is 3 units per atom. As there are 4 atoms, 12 electrons are to be added because the reaction is a reduction half reaction. So, plus 12 electrons gives 4 PH3 plus 12 OH minus. Now, charge is also balanced. Now, applying the same procedure to the second half of the reaction, P4 gives 4 HPO2 minus, that will balance the element. Then coming to oxygen, on product side 8 oxygens are present. So, on the reactant side we will add 8 water molecules. Oxygen is balanced. Now, coming to hydrogen, on reactant side 16 hydrogens are present, whereas on the product side 4 hydrogens are present. So, the product side is deficient by how many hydrogens? 12 hydrogens. In order to balance the hydrogens, we will add required number of water molecules on the deficient side and equal number of OH minus ions on the opposite side. Now, hydrogen is balanced. As water is common, this step can be simplified as P4 plus 12 OH minus gives 4 HPO2 minus plus 4 H2O. Now, balancing charge, for phosphorus the change in oxidation state is 2 units per atom. So, as there are 4 atoms and the process involved is oxidation, the electrons are represented on product side. So, before adding the two half reactions, see that number of electrons are equal in both the half reaction. For that purpose, multiply this equation with 2, this equation with 3. Adding the two half reactions, anything common can get cancelled. So, electrons they get cancelled. 5P4 plus 36, 24. So, here 24 water molecules are present, here 12 water molecules. So, plus 12 H2O gives 8 PH3 plus 12 HPO2 minus. Now this is the completely balanced equation. Next, types of redox reactions. Redox reaction is a reaction in which both reduction and oxidation reactions take place simultaneously. These redox reactions are classified as combination type, decomposition type, displacement type, disproportionation type, and proportionation type. These names are self-descriptive in nature. Combination means a redox reaction in which two or more elements combine together to form a product. Say for example, hydrogen reacts with oxygen to give water. In this, on the reactant side, hydrogen oxidation state is 0, oxygen oxidation state is also 0. On the product side, hydrogen oxidation state is +1, oxygen oxidation state is -2. So in this reaction, for hydrogen there is increase in oxidation state. So it is OHR, oxidation half reaction. For oxygen there is a decrease in oxidation state. So it is RHR, reduction half reaction. In this reaction, two elements, hydrogen and oxygen, are combining together to form a molecule water, in which both oxidation and reduction reactions are taking place. This type of redox reaction is called as a combination redox reaction. Then decomposition redox reaction is quite opposite to combination. Here a compound dissociates to give two or more than two types of products, and both oxidation and reduction are involved in the reaction. Say for example, hydrogen peroxide dissociates to give water and nascent oxygen. In this reaction, hydrogen oxidation state is +1, oxygen oxidation state is -1, because in peroxides oxygen oxidation state will be -1. On the product side, hydrogen oxidation state is +1, in water oxygen oxidation state will be -2. For nascent oxygen, oxidation state will become 0. That means for hydrogen there is no change in oxidation state in this reaction, but for oxygen in one instance there is decrease in oxidation state, in another instant there is an increase in oxidation state. So this is RHR, reduction half reaction, this is OHR, oxidation half reaction. So here a compound hydrogen peroxide is undergoing decomposition to give water and nascent oxygen as the products, and in this reaction both reduction is involved as well as oxidation is also involved. Such type of redox reactions are called as decomposition redox reactions. Displacement redox reactions. The redox reactions in which one element is displaced from its compound by another element, the reaction is called as displacement redox reaction. These displacement redox reactions are further classified into two types as metal displacement redox reactions and non-metal displacement redox reactions. As the names indicate, here one metal is replaced with another metal. Here one non-metal is replaced with another non-metal. General principle is a metal with a high electropositive character can displace another metal with a low electropositive character from its compound. When it comes to non-metals, more electronegative element can displace less electronegative element from its compound. Say for example, when few pieces of zinc are added to copper sulphate solution, copper being less electropositive than zinc will be replaced. So, this is an example for metal displacement redox reaction. Here zinc oxidation state is 0, copper oxidation state in copper sulphate is +2, on the product side zinc oxidation state is +2 while copper oxidation state is 0. So, for zinc there is an increase in oxidation state, oxidation half reaction. For copper there is decrease in oxidation state. So, it is RHR, reduction half reaction. So, it is a redox reaction in which metal displacement is taking place. So, can be taken as an example for metal displacement redox reaction. So, in this reaction the blue color of copper sulphate is slowly faded away because copper sulphate gets converted into zinc sulphate which is colorless in nature. For non-metal displacement reaction, we can take up this example. Through sodium chloride, if fluorine gas is passed, you will get sodium fluoride and chlorine. In this reaction, chlorine oxidation state is -1, fluorine oxidation state is 0. On the product side, fluorine oxidation state is -1 while chlorine oxidation state is 0. So, here chlorine oxidation state is increasing whereas fluorine oxidation state is decreasing. So, this part of the reaction is oxidation half reaction, this part of the reaction is reduction half reaction. This is an example for non-metal displacement redox reaction. Here fluorine is more electronegative than chlorine, hence it can displace chlorine from its compound in the form of chlorine. This is non-metal displacement redox reaction. Disproportionation reaction. It is a redox reaction in which same substance on the reactant side undergoes both oxidation and reduction. Such a redox reaction is called as disproportionation reaction. Say for example, hydrogen peroxide dissociates to give water and nascent oxygen. In this reaction, oxygen oxidation state on the reactant side is -1, on the product side in water it is -2 and in nascent oxygen it is 0. So, oxygen is undergoing both reduction as well as oxidation. So, this is an example for disproportionation reaction. Comproportionation reaction is quite opposite to that of disproportionation reaction. In this type of redox reaction also same substance undergoes both oxidation and reduction. Difference is the substance undergoing both oxidation and reduction will be present on the product side, whereas in a disproportionation reaction it will be present on the reactant side. For example, hydrogen combines with oxygen to give water. In this reaction, on the reactant side, oxidation states of hydrogen and oxygen are 0. On the product side, hydrogen oxidation state is +1 while oxygen oxidation state is -2. So, in this reaction hydrogen is undergoing oxidation while oxygen is undergoing reduction. Now, as you can see, the difference between disproportionation and counterproportionation reaction is, in disproportionation the substance undergoing both oxidation and reduction is present on the reactant side, whereas in the counterproportionation reaction the substance undergoing both oxidation and reduction is present on the product side. So, this is an example for counterproportionation redox reaction. Let us discuss some of the previous entrance examination questions that were based on basic concepts in chemistry. It is a theoretical question. Assertion and reason will be given. You have to check whether the assertion is correct or wrong. Now, looking at the question, the given assertion is equal moles of different substances contain same number of constituent particles. Coming to reason, equal weights of different substances contain the same number of constituent particles. This is wrong, because number of particles depend on number of moles. Number of moles depend on weight as well as molecular weight. If weights are equal, there is no guarantee that gram molecular weights will be equal. That is why the reason mentioned here is wrong. So, A is true, but R is false. So, you have to select C as the correct answer for this question. Now, looking at the third problem, x grams of calcium carbonate was completely burnt in air. The weight of the solid residue formed is 28 grams. What is the value of x? This problem is based on the decomposition reaction of calcium carbonate. When calcium carbonate is strongly heated, decomposes to give calcium oxide and carbon dioxide. Carbon dioxide, being a gas, will escape out, leaving behind calcium oxide as the residue. So, the weight of residue is 28 grams, means you should take it as equal to the weight of calcium oxide formed in the reaction. 1 mole of calcium carbonate can produce 1 mole of calcium oxide. 1 mole of calcium carbonate means in terms of weight 100 grams. 1 mole of calcium oxide in terms of weight will be equal to 56 grams. As you are getting 28 grams of calcium oxide, the corresponding weight of calcium oxide will be 28 into 100 by 56. So, that comes out to 50 grams. The correct answer should be taken as D. What is the volume of oxygen required at STP to completely convert 1.5 moles of sulfur into sulfur dioxide? Sulfur with oxygen. When sulfur is made to react with oxygen, you will get sulfur dioxide. So, the molar relation required is between sulfur and sulfur dioxide. As per the balanced equation, 1 mole of sulfur can react with 1 mole of oxygen to give 1 mole of sulfur dioxide. Now, in the given problem, 1.5 moles of sulfur is reacting. So, how much of sulfur dioxide you will get? 1.5 moles only. Now, convert these moles into volume by multiplying with 22.4 liters. So, that comes out to 33.6. So, correct option for this problem is C. Next problem, x liters of carbon monoxide is present at STP. It is completely oxidized to carbon dioxide. The volume of carbon dioxide formed is 11.207 liters. What is the value of x in liters? Carbon monoxide on heating with oxygen gets converted to give carbon dioxide. The balanced equation is 2CO plus O2 gives 2CO2. So, 2 moles of carbon monoxide can react with 1 mole of oxygen to give 2 moles of carbon dioxide. The volume of carbon dioxide formed is given. 11.2 liters means it is equal to half mole. When half mole of carbon dioxide is formed, that means half mole of carbon monoxide is involved in the reaction. So, this half mole of carbon monoxide, if you convert it into liters, it comes out to 11.207, the correct answer, correct option being B. Here concentration is specified as Y and weight of sodium carbonate we need to find out. This problem is based on molarity. Molarity is calculated by using this relation. Weight of solute, it has to be taken in grams by gram molecular weight of solute into volume of solution in liters. So, molarity is given as Y, weight of solute is given as X, gram molecular weight of solute is 106 and volume of solution is 100 ml. So, 100 by 1000. So, Y is equal to X by 10.6 you will get, or X is equal to 10.6 times Y. This relation holds good with the third option, that is C. If X is equal to 1.06, Y can be 0.1 and then this relation will be satisfied. Therefore, for this sixth question, the third option has to be taken as the correct option. What is the volume of oxygen at STP required for the complete combustion of 32 grams of methane? This problem is based on the reaction of combustion of methane. During combustion, any hydrocarbon will be converted into carbon dioxide and water vapor. Therefore, the balanced equation for this problem is 1 mole of methane reacts with 2 moles of oxygen to give 1 mole of carbon dioxide and 2 moles of water vapor. Now, what is required is we have to calculate the volume of oxygen for the burning of a specific quantity of methane. So, molar relation is 1 mole of methane can react with 2 moles of oxygen. As methane weight is given, these moles are to be converted into weight. 1 mole of methane's weight will be 16 grams and for 16 grams to react completely, we require 2 into 22.4 liters of oxygen. The weight of methane given in the problem is 32 grams. So, 32 grams requires how much of oxygen? 32 into 2 into 22.4 by 16. So, that comes out to 89.6 liters. So, the correct option for this seventh problem is B. 40 ml of XM potassium permanganate solution is required to react completely with 200 ml of 0.02 m oxalic acid solution in acidic medium. The value of X is potassium permanganate reacts with oxalic acid in acidic medium to give. So, the relation required is between potassium permanganate and oxalic acid. As per the balanced equation, 2 moles of potassium permanganate react with 5 moles of oxalic acid. The law of titration is V1 M1 by N1 is equal to V2 M2 by N2. Now, you take one set of values for potassium permanganate, another set of values for oxalic acid. Now, substituting the available data, in place of V1 you take 40 ml, in place of M1, that is what we have to calculate, say X by number of moles is 2. V2 is 200, molarity of oxalic acid is given as 0.02, N2 value is 5. So, from this x value is equal to 200 into 0.02 into 2 by 5 into 40. The value comes out to 0.04 m. So, the first option will be taken as a correct answer for question number 8. In Haber's process, 50 grams of nitrogen and 10 grams of hydrogen are mixed to produce ammonia. What is the number of moles of ammonia formed? So, as per the balanced equation, 1 mole of nitrogen can react with 3 moles of hydrogen to give 2 moles of ammonia. Now, the data available in the problem says 50 grams of nitrogen is made to react with 10 grams of hydrogen. 50 grams means in terms of number of moles, it comes out to 50 by 28 and hydrogen 10 by 2, that is 5 moles of hydrogen is available, 1.785 moles. Number of moles of hydrogen, 10 grams of hydrogen is given. So, number of moles will be 10 by 2, that is 5 moles. 3 moles of hydrogen can react with 1 mole of nitrogen. Therefore, 5 moles of hydrogen can react with 1 mole of nitrogen can react with 3 moles of hydrogen. So, 5 moles of hydrogen can react with how much of nitrogen? First we have to calculate that. That comes out to 5 by 3, that is 1.66 moles. So, that much of nitrogen is available. So, 5 moles of hydrogen is completely reacting in this reaction. So, accordingly we get how much of ammonia, that is what we have to find out. When 3 moles of hydrogen completely reacts, we get 2 moles of ammonia. The number of moles as per the available data in the problem is 5 moles. So, that comes out to 5 into 2 by 3, that is equal to 3.33. So, for this problem, first option can be taken as the correct answer, that is 3.33 moles. A compound contains 12.7% of carbon, 2.1% of hydrogen and 85.1% of bromine. Molecular weight of the compound is given as 187.9. We have to calculate the molecular formula of the compound. So, to solve this problem, first we have to find out the empirical formula by following the standard format: serial number, percentage composition, atomic ratio and simple atomic ratio. The number of elements specified in the problem are 3: carbon, hydrogen and bromine. Carbon percentage is given as 12.7, hydrogen as 2.1, bromine as 85.1. The number of elements specified are 3: carbon, hydrogen and bromine. The percentage composition of carbon is given as 12.7, hydrogen as 2.1, bromine as 85.1. Next, we have to calculate the atomic ratio. Atomic ratio is calculated as a percentage composition divided with the atomic weight. Therefore, carbon's atomic ratio will be 12.7 by 12, hydrogen is 2.1 by 1.008, bromine is 85.1 by 79.9. To calculate simplified atomic ratio, we have to select the least value in atomic ratios, and with that we have to divide all other values. So, in the atomic ratios, the least value is 1.058. With that we have to divide the remaining 2 values. So, carbon's simplified atomic ratio comes out to 1, that of hydrogen 2.083 by 1.058, that comes out to 1.96. Bromine's simplified atomic ratio value 1.065 by 1.058, that comes out to 1.006. Now, these values are to be adjusted to their nearest integer values. Carbon, already we have got an integral value, no need to change it. Hydrogen 1.96 can be taken as equal to 2. Bromine 1.006 can be taken as nearer to 1. Therefore, empirical formula of the compound is CH2Br. What we have to calculate is molecular formula, and for calculating molecular formula, first we have to calculate n factor, which is calculated by using the relation gram molecular weight by empirical formula weight. Gram molecular weight of the compound is given as 187.9. Empirical formula weight we have to calculate from the available data. Carbon is 12. That of hydrogen is 2.016, whereas bromine is given as 79.9. The total comes out to 93.916. This gets cancelled by 2 times, so n factor is 2. When n factor is 2, molecular formula is calculated by using the relation empirical formula into n factor. Empirical formula came out to CH2Br. It has to be multiplied now with 2. So, the answer is finally C2H4Br2. The third option C. So, for the 11th problem, correct answer can be taken as C. 3.001 into 10 power 22 atoms of an element weigh 1.15 grams. The atomic mass of the element is. The atomic mass, also called as atomic weight, actually represents the weight of 1 mole of atoms. 3.001 into 10 power 22 atoms weight is given as 1.5 grams. So, find out what is the weight of 6.023 into 10 power 23 atoms weight. So, that comes out like this: 6.023 into 10 power 23 into 1.5 by 3.001 into 10 power 22. On simplification, this value comes out to 30.1049. So, as the exact option is not available, we should take the nearest value, that is D, 35.5 as the correct answer. Which one of the following is an example for disproportionation reaction? Disproportionation reaction is a redox reaction in which same substance undergoes both oxidation and reduction. So, one by one we have to check the options for this particular property. We have to check the oxidation state values. Initially, oxidation state of chlorine is 0. In OCl minus, chlorine oxidation state comes out to +1. In Cl minus, it is -1. So, in one instance, chlorine oxidation state has increased. So, it will become OHR, oxidation half reaction. In the second instance, chlorine oxidation state is decreasing. So, it can be taken as RHR, reduction half reaction. So, in this example, same substance is undergoing both oxidation as well as reduction. So, it can be taken as a disproportionation reaction. In the same manner, let us check the remaining 3 options also. In the second instance, silver oxidation state is only increasing. That means only oxidation is taking place. In the second reaction, zinc is undergoing oxidation while copper is undergoing reduction. In the last option, oxygen oxidation state is increasing, means it is undergoing oxidation, you can say. So, none of these options fit into the definition of disproportionation reaction. So, for this question, first option A can be taken as the correct answer. For the 16th question, at a T Kelvin, the ratio of kinetic energies of 4 grams of hydrogen gas and 8 grams of oxygen gas is. The kinetic energy of a gas is calculated by using the relation 3/2 nRT. In this, n represents number of moles. When temperature is kept constant, kinetic energy is directly proportional to number of moles. So, number of moles of hydrogen we have to calculate first. It will be 4/2, that is 2. Number of moles of oxygen are 8 grams is the given weight. Oxygen molecular weight is 32. So, it comes out to 1/4. Value comes out to 8:1. So, for 16th problem, the correct option is D, 8:1. The number of molecules of carbon dioxide liberated by the complete combustion of 0.1 gram atom of graphite in air is. Graphite is an allotropic form of carbon. So, corresponding equation is C plus O2 gives CO2. So, 1 mole of carbon reacts with 1 mole of oxygen to give 1 mole of carbon dioxide. 1 mole is equal to 1 gram atom. So, 1 mole or 1 gram atom gives 1 mole of carbon dioxide or 1 gram atom of carbon dioxide. In the given problem, 0.1 gram atom of graphite is taken. That means indirectly 0.1 moles of carbon is reacting. Therefore, quantity of carbon dioxide formed is also 0.1 moles. So, finally, the answer comes out to 6.023 into 10^22. Nearest answer can be taken as the third one, C. So, for this 17th question, correct option is C. Like this, problems are to be attempted in this basic concepts of chemistry.